Hello, my name is Edward Kim, and in this video I'll be breaking down and solving the 2015 AP Calculus BC FRQ number 6. As you can probably tell by the question number and the Taylor series on the screen right now, this question is a series question. More specifically, the Maclaurin series for a function f is given by the series below. The series converges to f of x for absolute value of x is less than r, where r is the radius of convergence of the Maclaurin series. Part A of the question asks us to find the radius of convergence r using the ratio test. The ratio test is a check for convergence used on infinite series and is given by the equation L equals the limit as n approaches infinity of the absolute value of the n plus 1 term divided by the nth term for some series a sub n. The value of L tells us the information that we need to know from the ratio test. The parameters of L are as follows. If L is less than 1, the series converges. If it's greater than 1, the series diverges. If it's equal to 1, it's inconclusive. Because we are finding the radius of convergence, we want L to be less than 1. With that in mind, we can now work on solving out the limit. Since we are only considering the n and n plus 1 terms, we can temporarily ignore the rest of the expansion for now. The nth term is given. To find the n plus 1 term, we can simply substitute every n term with n plus 1. Here, I slightly rearrange the expression using exponent rules. We can substitute the n and n plus 1 terms into our fraction limit, and we will find that many things cancel out. If you substituted the n plus 1 and n terms into the ratio, you would earn a point here. Be careful not to make the mistake of thinking that this limit equals infinity. Because the limit only concerns the variable n, the x variable in this limit can be taken out and rewritten as a coefficient. However, note that terms like x to the power of n cannot be taken out. Eventually, our limit equals the absolute value of 3x for which a point is earned. If you recall from before, we want the limit to be less than 1 in order for this series to converge. Thus, the absolute value of x is less than 1/3 and the radius of convergence is 1/3. A point is earned here for determining the radius. Here's a neat visualization of the radius of convergence. As we increase the number of partial sums, we can see that the graph appears to remain relatively tame before spiking to plus or minus infinity at some point. As the number of partial sums grows large, we can more clearly see that the x value at which this line diverges is at about x equals 1/3, which is our radius of convergence. It is important to note that whether or not the x value is exactly equal to 1/3 is not relevant, since endpoint behavior is relevant to the interval of convergence, not the radius. Part B of the question asks us to write the first 4 non-zero terms of the Maclaurin series for f', which is the derivative of f. Then, express f' as a rational function for the absolute value of x is less than r. There are two ways to approaching the first part of this problem. The first way is to list the first 4 non-zero terms of f of x and then take the derivative of those 4 terms with respect to x. We are given the first 3 terms. And then, we can use the nth term to determine the 4th term by simply plugging in n equals 4, which we find is 27/4 times x to the 4th. We can then take the derivative of these 4 terms to get 1 minus 3x plus 9x squared minus 27x cubed using the power rule. The second way to approach this is to take the derivative of the nth term and then find the first 4 non-zero terms. Let's begin by focusing solely on the nth term, and then taking the derivative with respect to x. A very common mistake to make here is taking the derivative with respect to n. Here, the only term that we are deriving is x to the n, and every other term can be treated as a coefficient. The derivative of x to the n is n times x to the n minus 1 by the power rule, and we'll find that the n in the denominator and the coefficient of the resulted n from the power rule will cancel out to yield negative 3 to the n minus 1 times x to the n minus 1. Starting with n equals 1, the first four non-zero terms are 1 minus 3x plus 9x squared minus 27x cubed, which are the same terms we found using the previous method. Either way of approaching the step earns 2 points for listing the first four non-zero terms correctly. The f prime we have right now is an infinite sum, and we want to rewrite this as a rational function for part 2. A rational function is defined to be a fraction of two polynomial functions. The first step to rewriting the sum is writing it in terms of n, where n starts with 0. We can start by noticing that the series is alternating, so we must include a negative 1 to the n term. Then, we can observe that each term has a coefficient of a power of 3, so we can now add the 3 to the n term. Finally, there's an x term that increases power for every increase in n, so we can add the x to the n term. You'll notice that all of these terms are raised to the power of n, so we can simply combine this into the infinite sum from n equals 0 to infinity of negative 3x raised to the n power. One known power series representation of a function is 1 over 1 minus x, which is equal to the sum from n equals 0 to infinity of x to the n. Though the College Board expects that you have this memorized, if you're interested in deriving this representation, you can do that by simply using the general term for any Taylor series written on the screen right now. Going back to our problem, the only difference between this sum and our previous sum is that negative 3x is raised to the power of n instead of x. So we can simply replace x with negative 3x into our function. Therefore, we get that our infinite sum converges to the rational function 1 over 3x plus 1. 1 point is earned for the correct rational function here. We can check our work by graphing both of them. Here the green line represents the series, and pink represents 1 over 3x plus 1. We can see that as the number of partial sums grows large, for this interval, the series converges to the rational function. Part C of the question asks us to write the first four non-zero terms of the Maclaurin series for e to the x, and then use this series to write the third-degree Taylor polynomial for e to the x times f of x. E to the x is a known power series and is equal to the sum from n equals 0 to infinity of x to the n over n factorial. Expanding the first four non-zero terms of the series yields 1 plus x squared over 2 factorial plus x cubed over 3 factorial. A point is earned in this step for simply expanding the first four terms of the Maclaurin series for e to the x. F of x is the given series with the first three terms also provided. In order to get e to the x times f of x, we can simply multiply these series together. Here, it is important that you use the foiling method to get the third-degree polynomial. Although it is definitely possible to multiply the general terms together to find the first four terms that way, keep in mind that the question asks us to find and use the first four terms of e to the x, not the general term. We can begin our foiling by starting with the first term of f of x. X times 1 is x times x is x squared, x times x squared over 2 factorial is x cubed over 2, and x times x cubed over 3 factorial is x to the 4th over 3 factorial. The same process is repeated for the next term in f of x, which is negative 3 halves x squared. Note that the terms with a power greater than 4 are in red and can be ignored, since we are looking for the third-degree polynomial, which only concerns x terms with a power of 3 or less. After foiling the first 3 or 4 terms of each series, we can add our x terms that have a power less than 3. After some algebra, we get that our third-degree Taylor polynomial is x minus 1/2 x squared plus 2x cubed. 2 points are earned here for the correct third-degree Taylor polynomial. If you found this problem challenging, here are some other problems and resources that you can use. The links to these will also be provided in the description of this video.